Hello! In this video, we are going to prove the following theorem. In a metric space, x comma d, each open ball is an open set. So let's first remind ourselves of some definitions. Given a set x and a function d, which maps each ordered pair of elements in x to a real number, we say that the ordered pair x comma d is a metric space if it satisfies the following conditions. First, for every two elements x and y in our set capital X, d of x comma y is greater than or equal to 0. Second, for every two elements x and y in our set capital X, d of x comma y is equal to 0 if and only if x is equal to y. Third, for every two elements x and y in our set capital X, d of x comma y is equal to d of y comma x. And finally, for every three elements x, y, and z in our set capital X, d of x comma z is less than or equal to d of x comma y plus d of y comma z. Right, so in that case, this ordered pair is called a metric space. The elements of x are called points, and d is sometimes called a metric or a distance function. So now, let's talk about the following definitions of these two types of sets in a metric space. So first, we have the definition of an open ball. So if x is any point and r is greater than 0, then the set S of x comma r is defined to be the set of all points y such that the distance between x and y is less than r. Right, so this set is the open ball centered at x with the radius r. And next we have the definition of an open set. So if G is a subset of our set capital X, then G is called an open set if, for every element x in G, there exists an r greater than 0, such that the open ball S of x comma r is a subset of G. Okay, so now let's get into proving this theorem. So to start out the proof, let's give ourselves an arbitrary open ball in our metric space. So let's say it's S of x naught comma r naught, where x naught is some point in our metric space and r naught is some positive real number. So by definition, S of x naught comma r naught is the set of all points y such that the distance between x naught and y is less than r naught. So we want to show that this set is an open set. So in the definition of an open set, we want to show that this statement is true, where we take G to be S of x naught comma r naught. So we want to prove that this statement is true. And since we're trying to prove a statement about every element in S of x naught comma r naught, let's give ourselves an arbitrary element of S of x naught comma r naught. I'll call it x. Now for x to be an element of S of x naught comma r naught means that the distance between x naught and x is less than r naught. Now the whole goal is to show that there exists an r greater than 0 such that S of x comma r is a subset of S of x naught comma r naught. So what should we choose r to be? Well, to figure that out, we could visualize what our open ball looks like, right? So it's kind of like a ball. So it's centered at x naught, so like that, and has radius r naught, right? So we can represent the radius like that, and x is some point in the open ball. Maybe it's right here. So then this is our point x. The distance between x naught and x, I'll indicate it like this. It's d of x naught comma x. We're trying to find an r greater than 0 such that the open ball centered at x with radius r is a subset of this open ball. Well, it seems that if our open ball centered at x looks like this, it would be a subset of our larger open ball. So we're going to take r to be the radius of this open ball. But the radius of this open ball should just be this length minus this length, or in other words, r naught minus the distance between x naught and x. So we're going to take r to be r naught minus the distance between x naught and x. Since the distance between x naught and x is less than r naught, that implies that our choice of r is positive. So our choice of r satisfies this condition. Now we want to show with this choice of r that the open ball centered at x with radius r is a subset of the open ball centered at x naught with radius r naught. So we want to show that this set is a subset of the set. So to do that, we'll give ourselves an arbitrary element of the set. I'll call it z. Now since z is an element of S of x comma r, according to the definition of an open ball, that means that the distance between x and z is less than r. The whole goal is to show z is an element of S of x naught comma r naught. And to do that, we want to show that the distance between x naught and z is less than r naught. Well, if we write out the distance between x naught and z, the idea is we are applying the fourth condition of a metric space, right? Essentially the triangle inequality condition, right? The distance between x naught and z should be less than or equal to the distance between x naught and x plus the distance between x and z. But then we know that the distance between x and z is less than r. So then this quantity is less than the distance between x naught and x plus r. But then we could substitute r for r naught minus distance between x naught and x. So this is just the distance between x naught and x plus r naught minus the distance between x naught and x. So that means these two distances cancel out. We're just left with r naught. So this shows through this chain that we have established here, the distance between x naught and z is less than r naught. So z satisfies the condition to be an element of this open ball, S of x naught comma r naught. So we have shown, given an arbitrary element, z, in S of x comma r, it follows that z is an element of S of x naught comma r naught. Therefore, S of x comma r is a subset of S of x naught comma r naught. And that is exactly what we wanted to arrive at. So we have proven this entire statement, right? Because putting this all together now, right? To show that this set was an open set, we have shown given any element x in S of x naught comma r naught, there does exist in r greater than 0 such that S of x comma r is a subset of S of x naught comma r naught, right? We have proven exactly this statement, which proves S of x naught comma r naught is an open set, right? According to this definition. So we've shown, given any open ball in our metric space, it must be an open set. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.